So here we see the night sky, and even the ancients knew that there was something special about the planet Mars. You know, as they looked up, everything in just the immense night sky would move together except for these 5 wanderers. And of those, one of them had this very distinctive color. And it wasn't just the sort of blazing red lamp that Mars put out that made it special. It was also its motion. So Mars would usually move eastward against the sort of backdrop of the fixed stars, but every couple of years it did this really bizarre thing where for 60 to 80 days it would kind of backpedal against the zodiac and it would move back to the west before it resumed its normal course. And from this, Plato even concluded that the planets must have free will. For what else could these retrograde expressions be if not just sort of expressions of free will? So now we know why that happens. It's sort of as Mars and Earth in their orbits overtake one another. And this happens every 26 months. So we go into this period called opposition, where Mars and the Sun are on opposite sides of the Earth. And when that happens, we have an opportunity to send spacecraft up to Mars. And this is something that we have been doing since the 1960s. And this is where my book kicks off, and this is where this talk is going to pick up as well. It's going to talk about this. This is our Mars family portrait put together by the Planetary Society. These are a representation of all of these different missions, flyby missions, landers, orbiters, rovers that have been sent to Mars to try to find out more. So this is what I'm going to talk about first. I'll tell you a little bit about the history of Mars exploration, where we are now in terms of the science and particularly the search for life on the planet, what we have to look forward to in the future. It's a tremendously exciting time because later this month, 3 new missions will rise up into the sky bound for Mars because we're entering one of those periods where Mars and Earth are going to come close to another. And then if we have time, I'll tell you just a little bit about my research and the kind of day-to-day work of an astrobiologist. And then hopefully there'll be lots of time for questions at the end. All right, so in 1965, there was the first successful mission to Mars. So NASA launched Mariner 4. And so this was, obviously a very heady time. You have, a lot of things going on with the Cold War and lots of competition was being played out, of course, in space. And this mission was a flyby mission designed to take the very first photographs of the planet's surface. And here you can see it. It kind of looks a bit like a jeweled pterodactyl. There it was being prepared at the Jet Propulsion Laboratory in California, just in this canyon north of Pasadena, where we still prepare most of our NASA missions to go off to the surface of Mars. It had the 4 solar panels there. And one thing that was really interesting, and not without a fight, was the idea that it was going to take photographs of the surface. And one thing that was really fascinating was there was a prevailing thought at the time by a lot of people that photographs, that's not science, that's just pictures. But there's this wonderful man called Bob Layton, who was a Caltech professor, and he was able to push for this idea that we really needed to see the planet's surface. And he invented this wonderful gizmo that could, the slow scan television camera that could return pictures, 21 pictures, and a little bit of a 20-second were returned in the end. And of course, we've never seen the planet's surface. And when those pictures started streaming back, it took 8 hours for them to get to California. They had to be caught and transmitted through these teletype machines. And everybody was just sort of waiting for bated breath. What were these pictures going to show? And the scientists and engineers that were at JPL just could not wait any longer. So this man named Dick Grom went out to a art store and picked up a bunch of pastels, and he decided there were these little strips of paper that the data was coming printed out on. And the computers, of course, in 1965 were very slow, and it took a very long time to compile the image. So they just started a giant color by numbers in the hallway where they just started filling in different colors. And, you know, he just happened to pick these red colors because they seemed to match the grayscale image. This wasn't coming back in color at the time, just black and white. And so they started trying to try to see what this first picture would look like. And of course, nobody knew what to expect. But what came back was really staggeringly disappointing. So this is one of the images. This is frame 7. So of those 21 pictures that were returned, that each took 8 hours to get here. But you can see that the surface was covered with craters, that it looked just like the lifeless moon. And there's this great quote. This is Isaac Asimov, who's speaking to a friend of his. Why didn't we think of craters? And it was not at all what was expected on the surface of Mars. And it had tremendous implications. It meant that there had been no plate tectonics on Mars, no active weathering. The aqueous processes that wear down our surface must not have been active, because this was an ancient surface that had been preserved. All of the pock marks of all of the impactors that had hit the planet's surface were still there. And it was the next day, like after these images came back, the New York Times declared that, you know, Mars was probably a dead planet, which really resonated tremendously. And, you know, this is what the surface was. And just to understand what we were imagining, or what the team was imagining at the time, was that the surface of Mars would look more like this, really. So this is the planning map that was used, that was generated in early 1960s in advance of the 1965 mission. There was a man named Earl Slipher who had spent his whole life taking photographs of Mars. He'd taken 100,000 of them over the course of his career. And he had compiled them together in this beautiful book that I have a copy of. And you'll notice something really interesting here, is that there are these geometric features that are crisscrossing the surface, even like in the 1960s, before the mission goes. And so what that is, in many ways, it's a remnant of the maps that were drawn at the turn of the century. And there was a period there where most of the literate world actually believed that life had been discovered on Mars in the form of these straight lines, these engineered canals that had been interpreted. So there was an Italian astronomer, Giovanni Schiaparelli, who had a little telescope, and he put it up at the top of his observatory in Milan. And one of these periods of opposition, when the planets came close to one another, in the late 1800s, he had looked up and he had seen, you know, what he was seeing, and the features that he was resolving didn't look like any of the previous maps he had seen before. And when he started drawing Mars, not only did he give the features these absolutely beautiful names that were drawn from antiquity and the arts and classics, many of those names which are still with us today, and which is why the surface of Mars is so evocative, just has these incredibly romance-filled names. That's because of Schiaparelli. But he also had this other legacy where he depicted these linear features. Now, they weren't nearly as linear as shown here, but there was an American, an heir of an American textile fortune named Percival Lowell. And in the 1890s, he received a copy of a book that a Frenchman had written, Camille Flammarion, and he had taken these maps by Schiaparelli, and he had sort of interpreted them in the most, you know, optimistic light. And of course, this was a time of massive canal building here on Earth. You know, we were imprinting the surface of our planet in ways that humans had never really done before. And Percival Lowell, who had studied astronomy among many other pursuits, he had been a diplomat in the Far East for a number of years. He had just returned to America. He read this book with just this tremendous excitement. He scrawled the word hurry inside the inside cover because, again, one of these oppositions was approaching in 1894, and it was going to be a particularly favorable one. And he just turned it into his life's work to investigate this idea of engineered canals on the surface of Mars. And he recorded hundreds of them, you know, in these images. And so this is one that he published in his book called Mars. And he interpreted them as evidence that, you know, Mars had advanced to this state where water was in short supply, but there must be some sort of benevolent oligarchy in charge because they had a planet-wide system with no sort of national borders where, you know, these canals could bring melting water down from the polar caps toward the equator. And so Lowell, you know, this is again, he had a real way with words, and he wrote beautiful books, and it really caught on, this idea that there was a civilization on Mars. And I just showed these two examples of soap companies that really took this to heart. You know, Mars's people, send us some soap, was the first message from Mars. And so there was this real fervor, especially around 1900 and the years slightly before and after, about this idea. And some people, you know, really caught on, like this one man, Houston, wrote this book, Riddle of Mars. He was, you know, a hydraulic engineer, and he really laid it out exactly how this entire canal system would work. And so this continued for a number of years, but then slowly the tide began to shift, you know, and one of the key moments in the canal hypothesis sort of receding was a set of experiments that were done by astronomers at the Greenwich Observatory. They took a bunch of schoolboys and they had an image, a very tiny image, just, you know, 6 centimeters across or so. They put it at the front of a classroom, and you can see the image on the left here. And of course, the boys, especially the ones that were further back in the classroom, naturally connected this random series of dots into straight lines. And they argued that, you know, these weren't actually linear features that we were seeing, but just kind of a byproduct of how the human mind worked. And so, of course, Lowell flew into this frenzy saying, you know, I'm being challenged, especially in these foreign periodicals. And photography and astrophotography was just coming online in a big way. You know, the first moon of another planet had been discovered using photography by a man named William Pickering, who had helped lead Lowell west to build this giant observatory in Arizona, where he said he would be far from the smoke of men, and he could look at the sky without, you know, the problems that the modern observatories in these big cities were really starting to have, you know, with the Industrial Revolution. And so he led an expedition down to Chile. Lowell financed an expedition down to Chile, and took all of these photographs, and they brought back these plates, and you know, and these were printed up in Cosmopolitan magazine, sort of with this whole article talking about how this objectively proves the reality of the canals. But of course, these images, as you can see, are incredibly small. But a small image like this, you know, as you can see in the center, was paired with a drawing, you know, with the idea that with this flickering night, with our atmosphere, the flickering little eddies, the turbulence in our atmosphere would keep us from seeing clearly the planet's surface. But this is really what it looked like. If you could look at it and you could catch it in a moment of good seeing before it wobbled away. And this was heralded by him as objective evidence. But as you can see, it didn't really hold up for long. And what's been so interesting is work of modern ophthalmology suggests that it might have even been maybe some retinal webbing in the retinal veins, sort of webbed in the back of our eyes, that sort of we were perhaps seeing remnants of those in terms of some of the structures that we're seeing. And again, perhaps that tendency to just kind of connect different lines that we saw. So even though the idea of the canals fell away in, say, 1910 and the 1920s, you know, planetary science was really relegated to a backwater for much of the first half of the 1900s because, astrophysics was coming on in a big way with Einstein's theories and big push in that direction. But the idea of planetary science, I'll just go back and show you. So like, even though well, this is taking a bit. Maybe I want it slow to connect the slides. Well, I was just going to go back to the planning map and show you again this idea of linear features on the surface had persisted. Perhaps they weren't canals, but there were a lot of people that felt for sure that there must be some sort of real feature there. And that's why even up until the 1960s, and in part because Earl Slipher was the one that made this book and the Air Force drew from that to make this planning map, there was the sense, and even the follow-up missions, Mariner 6 and Mariner 7, these were two more flyby missions that were sent off to Mars by NASA in 1969 with the idea of kind of trying to permanently settle this issue. Like, are there really no lines whatsoever on the planet's surface? And they did, no linear features whatsoever were seen. And here on this globe, you can see the swaths, the planet's surface that were imaged by these two follow-on flyby missions. And so again, it's a pretty small percentage of the overall surface, but no linear markings were seen, but also, again, a cratered world, which was continuing the sense of kind of disappointment that Mars must be a world that's locked in the past without much at all interesting going on. So I wanted to bring in Carl Sagan here, who's one of the most famous planetary scientists of all time, I suppose. And he was a young man at this point. He was studying with this eminent planetary scientist named Kuiper, who was at the University of Chicago. And he did a postdoc at the Yerkes Observatory. And he spent a lot of time thinking about what to make of these images. And in an early stroke, an early action that I think would foreshadow a lot of his creativity that would come in the decades to follow, he decided to take it on himself to compile images from weather satellites, which were now starting to circle the globe in the late 1960s and early 1970s. And he did them at the same resolution as those images that were coming back from Mars. And he showed that you couldn't see any trace of anything human, even though we lived in a world that was completely covered with, human habitation. And he even looked further at 100-meter resolution, taking 1,800 images that were compiled from the Apollo and the Gemini astronauts of Earth, looking back at Earth. And even in those, you had no sense that like Moscow or Peking or New York, any of these places were actual cities. And you'd really have to know what you were looking for to really understand, like if a track of a tilled field or a road or something, we were actually invisible at those resolutions was one of the main things that he concluded. And so he did not lose hope for what the future missions could bring. And fortunately, again, another opposition in 1971, the first mission to orbit Mars. And of course, once you go into orbit around the planet, you have much greater coverage and you can, stay there for a much longer time, taking pictures and doing measurements of the planet's surface. So this is the Mariner 9 mission. And there's some tremendously bad luck in a way. So of course, all of these opportunities, NASA was usually racing the Soviet Union, who was sending a mission at the same time. And there was a big, very competitive space race, though in terms of Mars and planetary targets, the United States pulled ahead quite quickly. But again, here was an opportunity where a Soviet mission was launched at the exact same window and was rushing off to Mars. And a tremendous dust storm began to gather, and it probably started very small with just one little delicate arc and then just engulfed the entire planet in a matter of days. And so the astronomers that were here on Earth were looking up at the planet's surface, and it just became a billiard ball, which is a real problem for a mission that's designed to map the surface features. And the Russians actually had a landed package that was split to deploy at the exact same time, but had no ability to wait out the dust storm, no ability to reprogram the computers on that mission to wait until the dust had gone. So of course that got sucked into a tempest, and the images that the Soviets were taking all came back just completely obscured, showing no features whatsoever. But the software on the American mission on Mariner 9, we were really fortunate in the fact it could be reprogrammed so that it could wait, the couple of months until the dust actually began to subside. And when it did, it was really quite remarkable. So if you see on the image on the left, there were these 3 dots. They were the first things that were really seen. And it was just so bizarre what these dots could be. And then someone on the science team announced, these are calderas of volcanoes, of giant volcanoes. And everyone was really taken aback, because this was a planet that was thought to be very flat. No sense of topography had been seen at all in all of the flyby missions that had gone so far. And the idea that Mars was a smaller planet, it must have had less heat when it formed. It wouldn't have had, the idea was that it wouldn't have had the kind of internal heating that would be required to sustain massive amounts of volcanism. And there was this idea that it was a very small, flat planet. But of course, that's exactly what those features are. 3 giant volcanoes in a row next to the largest mountain in the solar system. And somehow all of that we just missed with those first flyby missions. And so Mariner 9 began mapping the features, and it was really extraordinary. So Olympus Mons, shown here in the right, that's bigger than Arizona. And it's got an escarpment that towers as high as Everest over the surrounding landscape. It is this incredibly enormous feature. And it was one of these times, again, that, the Mars science community was thrown for a real loop about what was going on with this planet and how these features could have formed. And it wasn't just these. There was also this giant canyon in which the Grand Canyon could just easily slide right into a side channel, this gash that had ripped open near the equator on the planet's surface that went about 20% around the planet's, just kind of like a belt there around the planet's midsection. And beautiful, beautiful scenes that the Mariner 9 mission came back with. And the Mariner 9 mission was also able to image the same features. There originally had been an idea to send a pair of missions, Mariner 8 and Mariner 9, but they ended up only one of those was successful during launch. And so it went into a kind of compromise orbit so that it could do mapping as well as map some features and how they would change over time as the seasons progressed. But it was a tremendously successful mission. And not only that, we saw these features for ancient river channels, features that really could only be carved by the action of liquid water. And this is one shown here, just a sinuous riverbed. There were plenty of these that made these very distinctive shapes, and they meandered across the planet's surface. And the surface of Mars, from all the other measurements, was well understood at that time to be far beyond the conditions that would support liquid water. The pressure was too low. Most of the atmosphere was gone to space. The atmosphere was less than 1% of the atmospheric thickness we have here on Earth. And it was also just staggeringly cold. And so liquid water would not exist on the surface, but this told us that Mars must have been a very different place back in the ancient past if there had been conditions that had been clement enough to have liquid water on the surface. So again, a really big change. And this inspired a lot of excitement about the possibility of, if there was water, perhaps there was life, because there was, everywhere we look on Earth where we see water, we see life. And it was with that, the idea of a landed mission, the Viking 1 and Viking 2 missions were planned for the late 1970s. And the idea was that this would be the first mission to land on the surface of Mars. And so that came to pass. So here I'm showing the very first image of the Viking mission, another NASA mission returned from the surface of the planet. And one thing that I love about this image that you'll notice is that the sky is blue, and the sky is not that color. It was not that color on when this image came back, but the calibration hadn't been set quite correctly. That, it just been sort of adjusted so that it had this blue sky, when in fact the sky on Mars is filled with dust. It's a much more sort of reddish, it's a butterscotch kind of color. And this image was sort of quickly released and then pulled back as the engineers realized that they didn't have the color calibration quite correct. But again, it's one of these moments where I think it's easy to see what we know or see ourselves in the Martian landscape. And so as you can see, the landscape was pretty rocky, pretty barren. And this mission, these two landed missions, they also had orbiters along with them, were carrying life detection experiments, the very first ones that would be run on the planet's surface. And one of the wonderful things, so Carl Sagan is now moving into the prime of his career. He's part of the imaging team on the Viking mission. And throughout the preparation, he had these miraculous ideas, this incredible imagination coming to bear about how life detection should be done. And he argued that there needed to be a nightlight on these missions, and that we needed to do pictures, all kinds of pictures, that we might be able to detect life just from the images. And maybe if we didn't actually see the creatures, we might even see footprints that they left behind. And he had been espousing, these life detection experiments were really focused on detection of microbial life. But Carl Sagan said, well, there's also a scientific argument that could be made for much larger creatures, what he was calling macrobes. This idea that if you want to conserve your surface area to volume ratio, like if you're in a really cold place that's very, very arid, you're a tiny microbe, you've got a lot of surface area for not very much volume. But if you become much bigger, you have a lot less surface area compared to volume for you to lose that heat and moisture out of. And so he said that maybe macrobes could be favored on the surface of Mars, kind of like the polar bears that are, tromping around the tundra areas, these areas newly recognized to be habitats, in the 1970s. And so this was, again, one of the kind of fantastic ideas that we had about what we might actually see when we touch down on the surface of Mars. But sadly, no macrobes came along, and even the life detection experiments on Mars came up confusing and dry in the end. So they were designed to detect metabolism based on this idea of growth and respiration. And in the end, there were 3 life detection experiments. I'll go through that as well as a gas chromatograph mass spectrometer, which I spelled wrong here. It should be GCMS. And that was kind of more of the part of the chemistry package there, but it found no evidence of organic molecules, the building blocks of life, which was incredibly perplexing. But just to walk through these really quickly, there's one called the pyrolytic release experiment. And so the idea was that Martian soil was dumped into a chamber. It was exposed to CO2 and carbon monoxide, carbon dioxide, carbon monoxide. They were labeled with a radioactive C14. And the idea was that if you incorporated some of this, and you would convert it, say, like into biological material. So if you heat the soil after this process has happened, you'll break down those organics. You can look for the release very, very precisely of this radiocarbon marker. And then there's another experiment called the gas exchange, where you put the Martian soil into a sort of chicken soup with tons of nutrients, the kinds of things, you would expect life to like: amino acids, glucose, salts, vitamins. And you looked for these gases that were being released, as a result of bacterial respiration. And then finally, there was the labeled release experiment. So you put it into the chamber. Again, you've got these nutrients, glucose and sulfate. They're enriched. And you looked for gases that are enriched with these two that could be released by bacteria. And so all these were synergistic to some degree. And the idea was, well, even if there were larger life forms, everywhere we see large life forms on Earth, they're also associated with small life forms like microbial life. And so originally the idea was that you would expect that the controls would come back clean and the results you would see. And if there's no life present, you'd see no signal from any of these experiments. But what was actually seen was incredibly confusing. There was this huge burst at the very beginning of gas released. And, to the point where some of the people on the mission just thought, we should send out for cigars and champagne. We've detected life. But then it just sort of, it dropped off suddenly. And there just seemed to be something incredibly reactive in the Martian soil that was proceeding, on these incredibly quick timescales. And again, these oxides and superoxides were what were likely there in the Martian soil, which was concluded to destroy any organics present. And this was kind of the takeaway mainstream scientific conclusion that came out of the missions. And a big part of this was that this GCMS, this oven that was looking for organic molecules, which are these carbon-containing molecules, the building blocks of life here on Earth, there were none. And it was so perplexing because even some organics can be formed abiotically and they rain down from space, and there should have been at least some organics on the surface, but there were none at all. And so that was, again, a big blow for life. But one thing I should say is that all of these experiments were designed in this time where our understanding of biology was quite different. And it was only really in the 1980s and the 1990s that we realized that the vast majority of small life forms of microbes here on Earth, can't be cultured in a laboratory. They won't grow when you just put them into a chicken soup of everything you think that they've ever wanted. They won't reproduce in those systems, in those tiny laboratories, big laboratories or tiny laboratories on the surface of Mars. And I think that our understanding of biology continues to progress. So we're getting a lot better at thinking about how to design things. But at that time, we just didn't recognize that, there were so many microbes that wouldn't, the vast majority wouldn't actually be conducive to making this experiment work. But so let's fast forward now. The Viking results and a combination of factors. I think part of it was, there were these very high expectations. We're running the greatest experiment in the history of modern science, and that experiment kind of came back null. And then there was a period in which, there were other missions going out to outer worlds and the outer planets of the solar system. And there was one mission in the early 1990s that had a catastrophic failure, but all of these things came together that we really had no missions for 20 years. The exploration of Mars, every time the planet swung back together, like there were just no missions launched by NASA, by the Russians, by any country. There was the one in the early 1990s, but there were none that were successful. And so there was a 20-year hiatus, which was I think very disappointing for so many of the graduate students and postdocs who had trained on these early missions, and then there was just really nothing to do. But one very good thing sort of came out of that time. Some of those individuals kind of turned their attention to Earth and understanding how life survived in extreme environments, and the science of astrobiology, sort of morphed from what had been largely called exobiology in the 1960s and 70s and took on a life on its own, trying to understand the limits of life here on Earth and really what biology, the range and the diversity and all of the interesting, intricate mechanisms that different life forms had evolved to survive in very harsh environments. One of those environments is down in Antarctica, and there's of course lots of astrobiologists do work down there, including myself, but something different also happens down in Antarctica. It's the prime place that we find Martian meteorites. And it's not because more meteorites fall in Antarctica than anywhere else, sort of a rain comes down all around, but they become concentrated in Antarctica. If they impact into the flowing ice, they'll kind of go under the ice and they'll come back up near places like these mountains, the Transantarctic Mountains. And when they come back up to the surface, because they're dark and everything else is white, they tend to absorb a lot of heat and they stay there. And they just kind of collect in a place to the point where like most of the rocks that you see in certain parts of Antarctica are actually meteorites that have fallen at different times in the past. And so NASA and other folks, there's this group called the Antarctic Search for Meteorites, and scientists go down to Antarctica usually every year, and they get on their sea-doos and they roam around and they look for these black spots and hope that they're meteorites, and they collect them. And so folks were doing this back in 1984, and the first rock they found in 1984, they named ALH, which stood for the Allen Hills, 84, which was the year, and it was the first rock of the season, so it was 001. And this rock ended up having a larger-than-life sort of role. So at the time, the age was thought to be much older than it is now. We've refined our dating techniques, but this was thought to be right at the beginning of our solar system. 4.6 billion years ago, things got kicked off, and this was only 4.5 billion years old. So it was really just within that first 100 million years was the thought at the time, though now we know it to be younger. All of the gauge dating suggested that the rock had remained on the surface of Mars until about 16 million years ago. It was captured by Earth 13,000 years ago. It fell in Antarctica. It was covered with ice, exposed about 700 years ago, recovered in 1984. And so this rock, when it was brought back, went back to Houston, to the Johnson Space Center. And for a while, it just kind of sat there. It was misclassified as a diogenite from Vesta, which is in the asteroid belt. But so follow-up measurements, I mean, this is just showing some oxygen isotopes where you can see the Mars meteorites really do cluster separately from those rocks from Vesta. But some of the measurements that we were able to do on sort of the Martian atmosphere when it comes to things like isotopes and trace gases have really helped separate which of these meteorites are from different bodies in the solar system, especially being able to identify the dozens now, many over, that we've found over in the hundreds that we found from Mars. And so there was this idea that life might actually be present in ALH 8400. And I'll show you a picture in a minute, but there were 4 lines of evidence. And so anyway, it took a very long time for this rock to sort of be classified as a rock from Mars. And then this really lovely scientist named David McKay, who was working at Johnson Space Center, started investigating this rock and started finding these very fascinating things about it. One was the presence of these really interesting organics called polycyclic aromatic hydrocarbons, and they can form as decay of microorganisms. They also form kind of in the char on your barbecue. So there are ways that it can form both abiotically and biotically. There were these magnetite crystals that were really similar to the crystals that were produced by some terrestrial bacteria. There were carbonate globules, and within them there were these ovoid structures. And let me show you a picture of what those look like. So again, here are these polycyclic aromatic hydrocarbons, the PAHs, the magnetite crystals, which were so pure and so aligned. And there are lots of bacteria here on Earth that use these magnetite crystals, these magnetotactic bacteria, as kind of little tiny compasses. And the argument there was that these crystals are so perfect in a sense that, it seemed like they were likely or could be made by bacteria, though other people have sort of argued that point in some ways. But that is one of the pieces of evidence that really is still very enticing to this day, work by Kathy Thomas Kirpta down at JSC. And also partly this was how these things were spatially arranged. But look within these carbonate globules, you see these ovoid structures. And I think that that's what really caught on to the public's eye. And so you can see they aren't really green against a background. But the McKay team published a paper in 1996 that said that they took these 4 lines of evidence and they said, taken together, it seems the best explanation could be that this is evidence of ancient life in the planets, in the planet's early crust, in this rock ALH 84001. And there was this huge frenzy. So of course, NASA did not say life on Mars. NASA said, there's evidence and we need to continue looking at this. But the public really, for a while there, we got a taste of what it would be like if we did actually find life on Mars. And headlines ran around the world, and there was just this tremendous frenzy. Though in the years that followed, a lot of the morphological fossils were thought to be perhaps too small to represent living organisms, these tiny things only, a few millimeters across, 20 nanometers across. And could you really have all the kind of biochemistry and machinery in there? And the Martian organics, these pods, they could have been produced by non-biological processes. There were, some lines of evidence that suggested that there could be contamination while that meteorite was sitting there on the surface of Antarctica for so long. And I think it sort of, again, came down to this idea, this is a wonderful quote by Carl Sagan, extraordinary claims require extraordinary evidence. But one thing that truly is there is, this is another quote, without that paper, I wouldn't be working in the field. There were so many people that got excited about this potential discovery and then trying to untangle the different scientific threads. It really led to a renewed interest in Mars. And even though we were planning to return to Mars after that, we have now gone 20 years where basically at every opportunity we've had a mission launch, which has been just amazing. You look at the scientific returns we've received over the last 2 decades. But 1997 comes along and we usher in this new era of Mars exploration. And NASA says, we're going to have better, faster, cheaper missions, and the goal is going to be to follow the water. So every 26 months, again, at those times of opposition, there were opportunities to send missions. And the first 2 of these better, faster, cheaper missions were in 1997, the Mars Pathfinder rover, the very first mission to rove across the surface of Mars and of another planet. And this little Pathfinder rover was about the size of a suitcase. It came barreling in. It landed on July 4th. And it was really more of a technological demonstration, just to see, can we really do a rover? But it spent the summer poking around and taking some chemical measurements of rocks in Aris valleys, which was a really exciting thing for me. It was a big moment in my life because I was, in high school, like getting ready to go off to college, and all of a sudden Mars was opening up. And then there was also the Mars Global Surveyor mission, which was the real scientific heavyweight in terms of those 2 missions that year. So Mars Global Surveyor went into orbit around Mars. It was recapturing a lot of the scientific experiments that had been lost in the early 1990s when that Mars mission that NASA had sent, came within 3 days of the planet and lost signal. And so here we go. Here's Pathfinder exploring the surface. And then Mars Surveyor had so many different instruments, and it really transformed Mars into a completely new vision, a new vision of how it would work. And it wasn't just imaging, it was really looking out into different wavelengths beyond what the human eye can see, and mapping minerals, mapping how heat was pulled in and out of rocks, which can tell you which surfaces are rock and which ones are more loosely held together, like soils. And this is one of my favorite instruments. So again, here's Olympus Mons. This is the topography was rendered by this instrument called MOLA, the Mars Orbital Laser Altimeter. And my PhD supervisor is very active in this mission and this instrument. And this laser, this incredibly precise laser, was able to take hundreds of thousands of instrument measurements and bring back to, we had at the time, better topography, better resolution on the surface of Mars than we had on the surface of Earth, and we had these beautiful renderings of how tall things actually were. So, of course, not all of those missions that we've sent back to Mars have been a success. And actually, there have been a tremendous number of Mars missions, a little less than half, we're getting better as we go, that have failed, that have catastrophically failed. And in 1999, again, better, faster, cheaper missions go off, the Mars Climate Orbiter and the Mars Polar Lander. And both of those, unfortunately, met their demise. The polar lander had a jiggle, like when it was up in the sky, and the landing legs mistook that for touching down on the surface, and cut off the engine, so it just fell out of the sky straight and impacted onto the surface, thinking that it had actually touched down. And then this very embarrassing mistake where metric and English units were used by, NASA was using one and the contractor was using the other. And so the trajectory for the Mars Climate Orbiter, where it was supposed to enter into orbit, was not where it entered. It was 200 kilometers off. And so that one burnt up. And so we lost the Mars Climate Orbiter as well. And I'll say, like, a lot of these missions, as you can see in this diagram, so the red missions are the Russian ones, and the blue ones are the American ones, and then the light blue ones are the European ones. And then you even see the Indian mission more recently in green. But that outer edge of the diagram there shows all the missions that have failed. And especially at the beginning, it was a tremendous lot of them that did not make it. But fortunately, several of them did. 2001, we went back with the Odyssey orbiter and were able to do beautiful mapping. We looked at things like subsurface ice, but also, again, this is a remote sensing image, one of the beautiful images of Meridiani Planum, which is where we eventually touched down with the Opportunity rover. And this is, again, showing a thermal emission map. So those orange areas are very compacted. Those light blue ones are ones that are much less compacted. And then, gosh, another pair of missions in 2003 from the European Space Agency, one which was tremendously successful, and then sadly the little Beagle 2 lander, which was sent by the UK, was going to be an astrobiology mission. And it touched down, and there was a problem with the solar panels not opening, so it never actually was able to return data. It's been found in remote sensing satellite imaging now, and it looks very likely that those solar panels just didn't open the proper way, which is just a huge loss for the scientific community. It would have been such a cool mission, and again, like an ESA contribution led by the UK. But the same year, the Mars Express orbiter went into orbit and collected beautiful mineralogical maps, found hydrated minerals, all kinds of things, continues to return data. It's been a really exciting contribution from the Europeans. And then I thought I would spend a bit of the rest of the talk talking about rovers, in part because those are the missions that I know the best, but we've also, it's really quite something when you can set down on the surface of a planet and you're not just stuck. You can actually traverse to interesting things, and in some cases just keep traversing. So these are the Spirit and Opportunity rovers. These were sent by NASA in 2003, landed in 2004. And these are the first missions that I ever got to work on. I was in my first year of graduate school at MIT at the time, and I got to go out to JPL and work in mission control, and we would see these beautiful things. So here's an image of Endurance Crater, which the rover was approaching the edge of, and then all of a sudden this huge football field of terrain had been punched out by an ancient impactor, and you could see these incredible layers kind of laid down like the pages of a history book. So this is Opportunity dipping in. This is, again, Meridiani Planum was the place it landed. Beautiful sedimentary rocks, which we had never really detected on the surface of Mars, which could really allow us to read the history of the place. These were water-lane sediments mixed with aeolian, wind-blown sediments. There were shallow pools of water that existed in this place. And one of the really interesting findings here were there are minerals, diagnostic minerals that must have only formed in the presence of very acidic water. We're talking battery acid, acidic water, which had big implications for the search for life, of course. But that was one of the major discoveries that came out of this mission. Certainly not limited to that. So the Spirit rover lasted until 2008. Both of these were only designed to go for 90 days of exploration before they, sort of the nominal mission ended, and that was their expected lifetime. But Spirit continued for 4 years, and Opportunity just kept going until just last year. I mean, they went a whole, over a marathon of distance and covered real terrain going from crater to crater to crater. But I just cannot believe how incredibly long Opportunity lasted. It was really quite remarkable. And I should mention, of course, that there have been so many other missions, landed missions like the Phoenix rover and InSight, and orbital missions like MAVEN, and of course the Indian Space Agency sent their MOM mission just a couple of years ago and had fantastic results for just $60 million of investment. There have been lots of other Mars scientific findies coming through. Beautiful mapping. This is just a recent image from ESA showing some subsurface hydrated minerals. I mean, there's so much that's been going on, but two of the really big things that I wanted to end the talk on were just these mobile science laboratories. We've gotten to the point where we can send, we have so much access to the Martian surface, and we've spent so much time developing tools and techniques for exploration that now we can land something the size of a car on the surface, and we can go miles and miles and miles to try to find different, really interesting terrain. And so this is a picture of the Curiosity rover, which NASA sent in 2012, and it's a very, very exciting mission. It landed in the floor of Gale Crater. And so Gale Crater, you can see the landing site ellipse there. It's a really ancient crater, and in the middle, there's a mountain called Mount Sharp that rises higher than Rainier above Seattle. It's a tremendous stack of sedimentary rocks that records most of the history of the planet. And so this Curiosity rover has landed and now has traversed out through two of the major geological units and getting up to the sulfate capping unit very soon. It's been a tremendously exciting mission. And so here it is, just to give you a sense of the rover landscape. You can see the crater wall in the back distance. And so one thing that Curiosity has been able to do is to drill these samples and pull them into an analytical laboratory held in the belly of the rover. And so there have been, a couple dozen drill samples almost at this point, and the rover can take its instrument arm and pull up ground rock and then pull it back into the heart of the machine. One of the things that I've had the tremendous privilege of being part of the SAM team, the Sample Analysis at Mars, which is a GCMS that's been run out of Goddard Space Flight Center. It was put in the spacecraft. It's about the size of a microwave. It's a big part of the belly of the rover, but it's been looking for things like organic molecules, and we found all kinds of organic molecules. Again, the building blocks for life as we know it. And of course, that's not the only find. We've found really intriguing evidence for methane, most of which is created through biological processes here on Earth. We've seen all of the sort of essential elements for life present on the surface of the planet. And these mudstones that exist there, we've been able to drill into those and show that there was water at this landing site, but not only the kind of water we had seen back at Meridiani with the Opportunity rover, but sweet water, the kind of water that if you were standing on the surface of Mars all those billions of years ago, you might actually be able to drink, that was, sort of running knee-high, that would have been, just painting this beautiful scene of what the ancient past might have looked like. And all of this comes together to paint this picture of a very habitable world, one that was very similar to Earth around the time that life was getting started here. And so what is coming next? This is what we have to look forward to. So this looks very similar to Curiosity, but it's not Curiosity. It's a new mission, the Perseverance rover, which as soon as July 30th could launch from Cape Canaveral when a launch window opens. It was built on the same chassis as Curiosity, and that's why it looks so similar. But it's got a different suite of 7 instruments and this huge arm. It's like an outstretched lawnmower. You think the thing's going to fall over, but nope, the engineers have built it very solidly, so it won't do that. But the idea behind this mission is really, I should mention before I forget, it's going to have a little sidekick called Ingenuity, which is a little helicopter that's, again, a technology demonstration with the idea that if you could get up and you could have a view of the terrain, you could build these beautiful mesh models of the terrain maps that you would be able to use to do a lot of autonomous traversing. At this point, you can only sort of go as far as you can see, and only really as far as you can see well, to make sure you don't, fall off a cliff or such things. But this could help you. This kind of technology could help us see really interesting things to try to plan for, to go to in the future, and really maximize the exploration return. The Perseverance rover is going to land in this beautiful place. This is Jezero Crater, which is an ancient river delta, which has been just exquisitely preserved. And one thing about Mars is because, again, it doesn't have the same sort of tumultuous weathering that we've got here on Earth. We've lost so much of our ancient past. There are only a very few places on Earth where you can find billion-year-old rocks or older. But when you go to the surface of Mars, it's almost all ancient past. It's been very, very well preserved. And this is one of these features that seems very promising for sort of bringing together the types of biosignatures or traces of life that we might find. And so what this mission is doing is it's kicking off this breathtakingly ambitious campaign to actually return samples from the surface of Mars to Earth. And so here we've got just the very first part of this, which is a caching rover, which is this Perseverance rover is designed to collect samples about the size of a pin light and put them into a cache, which can be picked up by a future fetch rover that will come along and pick up those and throw them into a Mars ascent vehicle. And then another vehicle will come back and grab those samples and return them to Earth. The dates are not quite unknown, but the idea is that are not quite known, but the idea is that hopefully this can happen within the next decade with very strong international partnership. And I have to say, this is a real paradigm shift for how we think about astrobiology. We take these measurements, we have all these, this data that's coming back from rovers and from orbiters, but the idea of actually having samples from Mars in our laboratories where we can sort of hit them with everything we've got is tremendously exciting. And I should say that this is not the only game in town, so other countries are taking advantage of this opportunity as well. The Chinese are sending a mission called Tianwen-1, which means questions to heaven. It's an orbiter, a lander, and a small mobile rover that will launch from Wenjin very soon when the window opens later this month. And the UAE, the United Arab Emirates, are launching a mission, an orbital mission, and this is really amazing. This mission's called HOPE, and the UAE didn't even have a space agency 6 years ago, but is already coming out of the gate with this planetary mission. It's really exciting to see all these new players getting involved. So not just NASA and the Europeans and the Russians, but the Japanese, the Indians, the Chinese, the UAE, and even private companies are talking about sending their own shots to Mars, their own sorts of missions, which is it's going to be a very interesting next few decades. So in addition to sample return, we've got these improving technologies, a really widening range of in situ targets. There's a lot of interest in drilling down into the subsurface. The surface of Mars in many ways is like a sterilization chamber. There's so much radiation on the surface that makes it sort of hard, most of us imagine, for extant life. But the idea of going down into the subsurface where the vast, at least half of our biomass is held here on our Earth within microbial form, very exciting target. We're also now able to peer into the subsurface and seeing things suggestive of subsurface glacial lakes, which would be wonderful to explore. One of the most exciting things that's happened in the last couple of years. And so I just thought I'll do this quickly because I want to make sure I leave plenty of time for questions. But, we've really evolved from this idea of following the water to looking for habitability. With Curiosity, we've really nailed the fact that Mars is an ancient habitable surface environment to looking for signs of life. And so this is one of the things I spend a lot of my time thinking about is how can we design tools and techniques to look for life in planetary environments. And I do it with like all these people. This is my lab. There are 12 of us now. Some of these folks are alums, but working together in this team at Georgetown. And I also work at NASA Goddard as a visiting scientist. We all work together to study things like biosignatures and planetary analog environments, learning how to look, how we can, you know, just deploy different instrumental techniques and tools to best use, best detect traces of life in places that bear very relevant similarities to the surface of Mars and other bodies as well. Exploring the limits of life, you know, for instance, down in these deep basaltic lava tubes where there's no surface light and life must survive in these primitive forms of life. Microbes survive on chemical sources of energy. And we also do work looking kind of at the persistence of life, these ancient biosignatures, these traces of ancient life that could be preserved. Antarctica is a great place to look because, again, it's so cold and so dry. It mimics in many ways some of the surface conditions on Mars where things can be preserved quite well. And then we take what we learn and we apply it to space exploration, not only trying to interpret data from current missions, but also devising instruments for future missions. And the idea, the goal, the ultimate goal would be to come up with something like this. For Star Trek fans, you might recognize these tricorders that can really just detect anything. We want to be able to have the technology where we can say, is this life? What is this thing that's in front of us? And I'll just mention quickly, one of the most exciting projects that we've been spearheading in my lab lately is this idea of looking for agnostic biosignatures or traces of life that don't presuppose necessarily the same sort of biochemistry or underlying molecular framework as life here on Earth. And one of the things I think that the book really delves into is time and again, we sort of expect things to be what we know. And, you know, it's very, very difficult to contend with the truly alien. And I think that trying to sort of think about, well, if life was, we know how to sort of find life as we know it, what if life was slightly different, or it took a different evolutionary path, or what if it was, say, sulfur-based life instead of carbon-based life? Like, how would we go about detecting it? Like, could we look for chemical complexity or unexpected accumulations of elements and isotopes? You know, just trying to be as inclusive as we can so that we can detect, you know, and all kinds of different life forms. So, of course, there is this possibility that there's no life on Mars. There's even a possibility that we've already brought life to Mars, especially some of those early missions were not perfectly well sterilized. And there's also a possibility that one day we will bring life to Mars. We might even colonize the planet and terraform it. But it's just, you know, even if there's no sort of the search for, if there's no life on Mars, the search for life will, of course, continue. There's so many interesting, intriguing targets here in our own solar system, these moons of Jupiter and Saturn in particular. And there's also this opening world of exoplanets. But I would still argue that Mars is the place that we can access and that we have the most, we can do the best science on Mars now. And even though it's this harsh world, if we find life on Mars, that just means that the whole universe must be positively teeming with life if that life came from a separate genesis.